Hi everyone, so another video. This time we're expanding on what we know about differentiation. So let's remind ourselves, we're saying that if y equals ax to the n, where a and n are constants, so a and n are any real numbers, then we're saying dy by dx is the power comes down and minus 1 from the power. Only in this situation, okay? And all things need to be in this form before you can use this. So therefore, if you had like an indice problem, let's say y equals x squared over x to the half, you can't use this because this is not in that form. You need to tidy it up first. So x squared divided by x to the half is the same as x to the 2 minus a half. So that gives us 3 over 2. This board's a bit naff to write on, so x to the 3 over 2. Okay, and then we could apply it. So therefore, dy by dx would be power comes down and subtract 1 from the power. Alright, that's why our indice work is so important, and that's why we keep going on about it. That's why it's in the assignment so often. Because you just can't, you cannot differentiate this like in that form. It has to be manipulated first, all right? So really, really important. Now, what is this? Well, remember dy by dx is the gradient function of a curve. Okay, so for example, if you started with y equals x squared, dy by dx equals 2x, doesn't it? You start with a curve, and the gradient of this curve is not constant. It in itself is its own function. So whatever value of x is here, your gradient has a corresponding value of x there. You see, as this curve gets bigger, so as we go along the x-axis higher up, it gets steeper and steeper and steeper, and therefore its gradient value gets bigger and bigger and bigger, which makes sense because this straight line gets bigger and bigger and bigger until infinity, or tends to infinity. Okay, let's go over this question here then. I've got this cubic here, and it's asking me to find the equation of the tangent to the curve at the point P. Well, that's exactly what differentiation does, isn't it? It finds you the gradient function. You've put in a specific value of x or y, so you put in a point, and it gives you the equation of the gradient, sorry, of that tangent at that point. So at the point x equals 1, I've got the curve here. There's the curve, it's a nice cubic. X equals 1 is here. So we're talking about this point here, and a tangent's going to look a bit like that, hopefully, okay, from the picture. But we're not always going to be given a picture, so let's pretend we don't. So I've got, for part A, y equals 3x cubed minus 2x squared minus 4x plus 1. So therefore, dy by dx, so implies dy by dx, power comes down, 3 times 3 is 9, 4 times 4x here, so the 2's come down to make 4, minus 4x, because remember that's x to the 1, 1 comes down, anything to the, so that leaves x to the 0, and anything to the power of 0 is 1. And now this plus 1 here, that just goes, that's gone, that's 0, because remember, think about it, if you've got a constant 1x to the 0, because remember x to the 0 is 1, if you differentiate just a constant, the 0 will come down next to the x, and that will produce 0 times 1, x to the minus 1, and 0 times anything is 0. So therefore, all constants differentiate to 0. To 0. Okay, really important. So, see a constant, just get rid of it. Therefore, we found the gradient function, which is a quadratic, but we want to know the specific value of the gradient at the point P at x. So at P, x equals 1, so we can find the gradient at x equals 1. Notice that notation there, that straight line notation. And now I can put that in. So 9 times 1 squared minus 4 times 1 minus 4 is the same as 1. 9 minus 4 is 9 minus 8. So that gives us 1. So we want the tangent equation at P, which has coordinates, and we need coordinates, don't we? Because we know we need y minus y1 equals m, which is our gradient, 1, x minus x1. And we know what x is, that's just 1, but we don't have our y value. Okay? So how do we get the y value without using the graph? Well, there's only one place where we can get it from, isn't it? Here. We know what x is, so therefore from here we can find what y is. So y equals 3 minus 2 minus 4 plus 1. So that gives us minus 2. So there's minus 2, and therefore I get y plus 2 equals that. So y plus 2 is x minus 1. You can forget about the 1 in the front, because 1 times anything is itself. Let's test how right or wrong I am then. How bang on that is. Y plus 2 equals x minus 1. Not bad. Nah. Put it down to scaling. Put that down to scaling. Okay, part B. Find the equation of the normal at P. Well, what's the normal? The normal corresponds to, if you've watched the mechanics videos, normal stands for perpendicular, doesn't it? The normal reaction is perpendicular to the surface. So the normal means the perpendicular to the tangent. So if I go back to this graph, I'm looking for, there's the tangent there. I'm looking for the line perpendicular to that tangent here. That comes in handy when you've got two curves which are at right angles to each other and you want to find their equations, etc. So we're looking for this, which is the normal. So remember, the normal is perpendicular to the tangent. Okay. So let's find that. We know that the gradient of something which is perpendicular, so part B, we know that the perpendicular gradient is 1 minus 1 over our tangent gradient. So therefore, m2 is minus 1 over our gradient, which we found was 1 at P. So therefore, m2 is minus 1. And we know that P had coordinates 1 minus 2. Therefore, normal at P, let's quote the coordinate, is y plus 2 equals minus 1, x minus 1. Easy, see? Once you found that tangent gradient, the rest is okay. Let's go for another one. This time we're talking about stationary points. Now, I think I've talked about this before. It says find the coordinates of the turning points. So you've got two things here. You've got stationary points and you've got turning points. What does that mean of this curve here? So let's first whack that curve into autograph then. So if we clear the ink there. Okay, so let's whack that one in. So we've got another cubic. There we go, there's our cubic. Right, so what's the stationary point and what's the turning point? Well, a turning point, well first let's investigate this curve. This curve here, what kind of gradient does it have? Well, it has a positive gradient, doesn't it? Because the graph is getting bigger, the y value is getting bigger, and then actually the y starts to slow down. Its increase begins to decrease until, slow down until we get this flat bit here. Now this point on the curve where we get a flat tangent is when dy by dx equals 0. This is a stationary point. Okay, a stationary point is when the gradient equals 0. And then the gradient becomes negative, negative, and then bang, we reach this other point, a stationary point, because our tangent has gradient 0. And then we've got a positive, right? So a turning point is when your gradient turns or gradient changes sign. So when it goes from positive to negative or negative to positive, okay? So this clearly positive gradient to negative gradient either side of a stationary point, then this is a turning point and this is a turning point, all right? Because our gradients change sign. So one of these things is called a maximum. So this would be what's called a local maximum, right? Because it's the maximum on that section of the curve before it turns and then starts getting negative again. And this thing would be a local minimum because it's the lowest point of that turning point before the graph starts increasing again, okay? So there we go. Maximum points, minimum points, turning points, stationary points. We've classified them all. So let's go for that. We've got this curve here, and we're going to try and find the coordinates of the turning points on this curve. So we've got y equals x cubed plus x squared minus x plus 1. We know to find any gradient, we need to differentiate. So 3x squared plus 2x minus 1, and remember all constants go to 0. This thing equals 0 then at stationary points. So you can write at SP, do you see? Very important that you're saying why this thing is 0. And now you can solve, can't you? So if we want to find the coordinates of the stationary point, we could factorize, let's say, 1 and 1. So this will be plus and this will be minus. And now we can solve to say x must equal a third and x must equal minus 1. But we're looking for stationary points, so therefore coordinates, not just x values. So if we put this in, where do we get that y value? Well, the only equation on offer, like before, was the original. So y equals a third cubed plus a third squared minus a third plus 1. So use a calculator, use that magic answer trick. So type in a third and then answer cubed plus answer squared minus answer plus 1. So that's 22 over 27. And minus 1, so answer cubed plus answer squared minus answer plus 1 is 2. So, good. Okay, so stationary points we can now put in coordinates. And there we go. There we go. Cool. We've discovered our stationary points, and that's a nice way to finish off that question. Part B, though, is to classify them. So even though from the picture I can see which one corresponds to the maximum or minimum, I mean, obviously this must be the third on the x-axis, mustn't it? And the 22 over 27. So this one must be our minimum. And this one is our maximum, which we know is at minus 1 and 2. You can see that. You can see that's the case there, right? But if we didn't have the picture, how do we know which is the max or min? And that's where we would need to differentiate again. So you could write, to classify, we will now look at the second derivative, okay? So the second derivative, what we're saying is, we have dy by dx, we had that, but now we are differentiating again. So this d by dx means differentiate with respect to x again. So this is now d squared y over dx squared. So notice dx times dx, that's dx squared, and your d times d is a squared, and then you've got your y there. It doesn't really work in that way, but in the end, you can manipulate them like you can fractions and multiplication. So I'm going to differentiate this thing, this thing again. So you're saying dy by dx equals 3x squared plus 2x minus 1. And now you differentiate this one again. So this will be 6x plus 2. Okay, so this is your second derivative. Why do we need the second derivative? Well, if we go back to displacement and velocity and acceleration, so if you had here's displacement, so in other words, kind of distance from a starting point, and then if you found the change in distance over change in time, that would be your velocity, wouldn't it? Okay, so displacement, velocity, and then if you differentiated this again, so in other words, what's the change in velocity over change in time? You would get, if this was y equals 2x, then this would be y equals 2, and you would get a straight line, i.e. the acceleration is constant. So the change in velocity, the gradient of velocity is constant, okay? So the second derivative tells you whether you are beginning to, whether you've reached a max or min. So it's telling you, like, what's the rate of change of your rate of change? Do you see? So if your rate of change of your rate of change is positive at a point, then therefore you must have a minimum, because your function is beginning to increase its velocity again, right? So if your acceleration is at its minimum and then it's starting to get bigger and bigger and bigger, then therefore you must be increasing your velocity, and therefore your gradient must be going positive, okay? So let's let's think about that, right? You had your cubic function here. We then differentiated it once, which gave us a quadratic, okay? So this cubic started like how we had it before, like that. And then we differentiated it and we got a quadratic. And let's just see on autograph what that quadratic looks like. So if I put it on here, y equals 3x squared plus 2x plus 1, so minus 1. You can see that blue curve here. It doesn't look that clear, does it? But that blue curve here, can you see it? The quadratic running all the way down here. Now, if we then differentiated your quadratic, you would get the straight line, which is what we've produced here. That's 6x plus 2. Because think about it, the rate of change of that curve is either positive or negative at a point, isn't it? So if we take the points that we have, the stationary points, that's what we care about. Well, what's happening at x equals a third, d squared y over dx squared is going to be 6 times a third plus 2, which equals 4, which is greater than 0. Therefore, we have a minimum at this point. So this is a minimum because your rate of change of your rate of change is positive. So if I look at a third here, here's roughly a third. I know it's getting a bit messy now, but here's the point of x equals a third. You can see that the gradient of this function is positive, isn't it? The gradient here, so our d squared y over dx squared is positive, and therefore it's increasing, which is at this point here that we were looking at earlier. The gradient is increasing, and the gradient of the gradient is increasing, and therefore it must be at a minimum point because it's at its lowest point. Whereas the other one, so if now we say at x equals minus 1, d squared y over dx squared equals 6 times minus 1 plus 2, which equals minus 4, which is less than 0. And again, that must mean we have a maximum because our acceleration is now decreasing. So our velocity will start to decrease, okay, after that point. So it must be its highest point. Look at that one. Look at our original curve here. This one here. What's happening after that point? Well, you can see that the gradient's becoming negative. And the rate of change of our gradient function at this point here, you can see that the gradient is negative. The graph is getting lower. Hopefully you can see what's kind of happening there. Okay, so that is our final answer there when we write down our stationary points and we classify them. And we classify them by looking at inequalities like that. So it's the opposite of what you'd expect. If it's more than 0, it's a minimum. If it's less than 0, then it's a maximum. Okay? Right, I think that'll be it for this video.